In this video, we're going to pick up where we left off with the data loading, and we are going to explore the actual setup of a detailed event fitting and analysis run. So if you recall from the last video, as soon as we started a new analysis, we got this new control panel set up, as well as some fitting of the baseline. And we're going to go through each one of these parameters one at a time to make sure that it's clear what each of them does. Now, this is going to be a fairly long video because there are a lot of parameters to set up. Not to worry, you only have to do this initial setup once. Most of these parameters are specific to the hardware and acquisition settings that you're using. Assuming those don't change significantly between each experiment, you'll only actually have to set most of these parameters once. And the next time you do this, it's going to be much simpler. There will only be a handful of numbers that need to be tweaked. But for now, we're going to take advance and we're going to go through all of these one at a time. So at the start, the fitting setup control panel is going to open at IO settings. This is where we tell Nanolyzer the details of the experiment we set up. So the sampling frequency, this is set at the time of the experiment. For NNi binary files, by default, we use 500 kilohertz. If you're analyzing a Chimera VC100 data set, this will be 4.167 megahertz. And ABF files, this will typically be encoded in the ABF file itself and detected automatically. So this is a setting that is set experimentally and should simply be updated to reflect whatever your experimental setup uses for sampling frequency. The chunk size parameter refers to how much data Nanolyzer is going to read in one segment as it progresses through your file, finding and fitting events. 1 second is usually a safe bet. You can make it a little bit longer, where Nanolyzer will take a little bit more memory to operate. You can make it a little bit shorter if you want. The general way that Nanolyzer proceeds is it's going to read through your data one chunk size length at a time. It's going to find all of the events, flag all of those event locations, and then it's going to go back later and fit them. This chunk size won't affect actually finding events. For example, if there's an event that happens to straddle the edge of 2 chunks, that's not a problem. So don't worry about that for high density data. It'll still find those just fine. The trade-off here is that if you have, for example, a very noisy baseline with a lot of low frequency noise, you typically want to set the chunk size to be relatively small so that the baseline is roughly constant over each segment that you're analyzing. For very clean data like this, where the baseline doesn't change significantly, you can use a larger chunk size. 1 second is usually a reasonable setup. The only caveat here is that you want to make sure you're capturing the full bandwidth in each data segment. And so if you're sampling at 500 kilohertz, you probably don't want to go too far below 1 second if you can avoid it. The read whole file tick box is relatively self-explanatory. If it's ticked, Nanolyzer will analyze the entire data file or entire data set. If you're using Chimera VC100 files, for example, where they're split up, it will concatenate all of them, ordered by timestamp, and treat them as one continuous file. If for some reason you don't want to analyze your full data set, you can untick this and you can set a start and end time. Nanolyzer will then only analyze the file on that segment. Today, we're going to use the whole file. Once you're satisfied with that, we go to event segmentation settings. Now, these settings refer to use of or finding events in the file. We're not fitting them yet, we're simply finding them. So event direction, 0 blockage 1 enhancement. Most of the time, this is going to be 0 since the vast majority of Nanopore experiments involve blockage of the current. But if you're using very low salt concentrations, for example, you might be looking at current enhancements, in which case you could set this to 1 and proceed with analysis that way. The minimum and maximum baseline values in picoamps, you'll see have already been filled out. And these are the top and bottom of this transparent green box that's being displayed here. This is automatically fitted as part of the new analysis setup. If for some reason the fit isn't good, if you don't like the fit, you can change these. For example, if I want to make the minimum baseline negative 5,500, oops. Take out to a different box. And after a second or so, you'll see that the display updates to reflect that change. Generally speaking, this fit is going to be good, and if you notice significant issues with it, by all means submit a bug report so that I can fix it. Manual baseline override tick, by default, this is off. If for some reason the baseline fitting is simply failing, you can tick this box and set a mean and standard deviation manually, which would otherwise be displayed up here. For the most part, you won't need to do that. Detection threshold refers to this red line here, and this is in units of standard deviations of the baseline noise. So a setting of detection threshold 15 means that in order for an event to be called, in order for the start of an event to be called, the current has to deviate from the mean baseline by at least 15 standard deviations. And whatever point that passes that 15 standard deviation mark will be flagged as the start of an event. If you want to change this, change it this way, tick out somewhere else onto the controls, and after a brief delay, you'll see that the threshold line is updated to reflect that, as well as the hysteresis value. The hysteresis value is used to flag the end of events, and it refers to, again, standard deviations of the baseline current referred from the threshold value you set before. So a detection threshold of 20 and a detection hysteresis of 21 means you need to go 20 standard deviations away from the baseline for the start of an event to be called, and then you need to go 21 standard deviations back toward the baseline mean, so just past baseline mean, in order for the end of an event to be called. And the vast majority of the time, you're going to want detection hysteresis to be one more than detection threshold, which just means that you need to go all the way back to the mean and slightly past it in order to call the end of an event, and this just avoids false negatives on the end of events. You can, if you want, change hysteresis to be something other than threshold +1 by manually editing it. For the most part, this won't be necessary. Use data filter tick box refers to whether or not you want QSUM to internally apply the same filter, or a different filter for that matter, as the one you have labeled up here. If this is off, then when QSUM is going through behind the scenes to detect your event locations, it's simply going to use the raw data. If you want to turn the filter on, you can tick this box and update the cutoff frequency to be whatever it is you want. We're not going to use a filter for this one because this data set is sufficiently clean with the raw settings. Once these are set up, go to event fitting settings. So the event segmentation section refers to how it's going to go through to find those events. Event fitting, once it's found the events, then actually goes through and attempts to fit a piecewise constant signal to your DNA data. And here we have a number of settings that interact in interesting ways. And so we'll go through these one at a time as well. Sensitivity is one of the only numbers that's going to need to change between every run. And if we turn off advanced, you can see these top three here are still accessible and still editable. These numbers are going to need to change each run. Everything else can essentially be set and left, but these are going to have to change. And so to explain this, I'm going to zoom in on one of our events here. Oops. Where you can find a folded event, because that's the simplest way to demonstrate this, and I think we're in luck. So yes, here we have a multi-state event, assuming we actually want to fit this one here. The sensitivity parameter, again, is multiples of the standard deviation of the baseline current, 56.5 picoamps here. And sensitivity should be set to the smallest significant change in current that you want to be fitted as a significant step in your event. And we'll unpack that sentence in a moment. So for this event we have highlighted here, there are 3 step events: from the baseline to the folded block state, from the folded block state to the unfolded block state, and from the unfolded block state back to the baseline. So the size of this difference here, 3,800 to 5,200 picoamps, so that's about 1,400 picoamps. The difference between the folded and unfolded states is about the same, about 1,400 picoamps. And then obviously the combination of the two is about 2,800 picoamps. So the smallest step change that we see in this event corresponds to about 1,400 picoamps. The RMS noise of about 50 picoamps, just over 50 picoamps, means that the sensitivity we want to set for this is the ratio of those two. And the ratio of those two is quite simply 1400 divided by the 56.5 peak ramps, which comes out to about 25. So we set sensitivity to 25. The minimum step size refers to the size of step changes that we want to suppress, that we want to ignore. Because we use a statistical approach to fit these events in the background, if you have just a flat baseline with no event in it, eventually it's going to trigger a change that's going to look very, very small. And so we want to suppress events that show very, very small step changes. Typically, you would set this equal to half of the sensitivity. So we'll set this to 12.5. The elasticity parameter is something that can change run to run. For the most part, will stay at 0. And the idea here is that if you have a data set that has very, very fast events and very, very long events, and here I'm talking a difference of orders of magnitude. If you have events that are 10 microseconds long at one extreme and milliseconds long at the other extreme, it will tend to overfit the very, very long events unless you change the sensitivity and make the sensitivity length dependent. And so an elasticity setting of 0 means don't pay any attention to the length of events. They're all close enough. They're all within an order of magnitude or 2 of one another, and there's no need for a sensitivity change. If you set this to anything non-zero, let's say 10, then elasticity will be added to sensitivity for long events in the data set. So the short events will be fitted with a sensitivity of 25. The long events will be fitted with a sensitivity of 25 plus 10, 35. And that just helps mitigate the overfitting that will otherwise happen with very, very long events. For this data set, as we're going to see, it's relatively tightly distributed in time, and so there's no need for the use of the elasticity parameter, but that is another one you can change. Minimum step separation refers to the rise time of your system. So this is, for the most part, a hardware parameter that's determined by the RC constant of the combination of your electronics and your nanopore chip. And this is measured in microseconds. And what this does is it ensures that if a step change is detected, we wait at least, in this case, as it's set up now, 5 microseconds before allowing another step change to be detected. And this happens because while in principle, nanopore translocation signals are perfectly piecewise constant, in reality, of course, baseline distorts these signals a bit and you get this rise time. You get a non-zero number of data points in the middle, going from the bottom to the top of this event. And you just want to set the minimum step separation such that it spans that rise time. So here we have maybe about 10 data points separating these two at 2 microseconds per data point because of our 500 kilohertz sampling rate. That comes out to a 10 microsecond rise time that we want to ignore. And so we can set our rise time to 10 microseconds, which will say, once you detect the step change here, make sure you don't detect another step change until at least here. And that'll ensure that we don't fit a staircase to our signal. Internal detection threshold and internal detection hysteresis are very simple parameters that are just for bookkeeping. They don't affect the fits themselves. All this will do is that anytime the current deviates from the baseline by, in this case, 6 standard deviations, Nanolyzer will count. We'll add 1 to a counter. Anytime it returns back toward the baseline by, in this case, 3 standard deviations, it will add another 1 to that counter. And the idea here is that using this, we can categorize events by the number of times they cross these thresholds, which can be useful for event filtering later, which will be the subject of a future video. But these won't affect the fits at all. And if you're not interested in counting threshold crossings in your events, you don't need to worry about them. You can set them to whatever you want, and it's not going to matter. Baseline wait time is another parameter quite similar to the minimum step separation. And typically, you just leave it at 0. The idea being that in some sort of exotic nanopore systems, you can get ringing in the baseline as an event actually leaves the pore. And you can tell Nanolyzer how long to ignore after the event end is called to avoid overfitting that ringing that typically isn't indicative of molecular properties. And finally, the nonlinear fit threshold is a very important parameter because internal to Nanolyzer, there are 2 approaches to fitting. One is the statistical piecewise constant signal fitting to which most of these settings pertain. The other is a nonlinear fitting algorithm that's used to fit for very short single step events. And the nonlinear fit threshold determines the length of event, or it determines which algorithm is used to fit depending on the length of event, whether it's longer than nonlinear fit threshold, in which case we use the QSUM algorithm, or shorter than nonlinear fit threshold, in which case we use this nonlinear fitting algorithm, which you might be familiar with from other nanopore analysis softwares. And typically, you want to set this such that all of the events that are faster than this parameter have only a single step in it, because the nonlinear fit is specific to single step events, be that folded or unfolded, or whatever that means for your molecule. And generally speaking, you would set this to 2.5 times larger than the minimum step separation, which 25 microseconds for this time. The attempt recovery tick box says if you have a long event and for whatever reason the statistical fitting approach fails, you can try again using the nonlinear fit method, and we'll use that. Use event filter, again, allows you to set a different low pass filter, a low pass Bessel filter, during the event fitting stage. So whereas event segmentation settings, you can set up a filter to be applied when you're looking for events. The event filter allows you to set up a different filter if you want for the actual fitting process. But again, for this data set, we're going to leave that off. Once you've set these up, again, all of these parameters are going to stay generally the same between runs. You only have to do this setup once. The only thing you need to change the next time you run the analyzer is going to be the sensitivity, minimum step size, and potentially the elasticity, depending on the details of the molecules that you're actually analyzing. And last but not least, event rejection criteria. These are very, very simple. If you have very short events that can't be fitted, throw them out. I usually set this to be equal to my minimum step separation. Anything shorter than that, I'm not going to be able to fit accurately anyway. Maximum event length. This is just useful for getting rid of clogs. In this case, 50 milliseconds is a very generous cutoff. I don't need anything really that long. I'll set it to 10 milliseconds. Where anything longer than that is simply going to be rejected. We're not going to try to fit it. We're just going to let it be thrown out in the analysis. Once you're done with that, you're satisfied with all of your fit settings, you simply tick save and run analysis. And as soon as you do, you're going to see that this command line is going to pop up a progress bar. There are 2 stages to it. The first one, we go through and we locate events using our event segmentation settings. And you can track along, see how many of the segments that you're looking at have good baseline detected. And just make sure that this is a reasonably high number for your data set. This obviously is an excellent data set with a very clean baseline, and so I expect the entire thing to be accurately fitted. If you have a pore that's clogging or noisy, for example, and you have areas of baseline that fall outside of the baseline bounds you set, you might see this number be smaller. Whether that works for your data set is a context-dependent question that you need to decide for yourself. Once it's done going through the baseline, it'll give you a report. It found, in this case, 470 events, successfully fitted about 91% of them and failed on 9%. It used the statistical algorithm for most of them, used the nonlinear fit algorithm for only 5 of the 427 events it successfully fitted. And for all of the fit failures, it tells you why it failed. So code 242 baseline differs. So this means that for 42 of the events, when it was going through and fitting, it found a different baseline before and after the event by a margin of at least 2.5 standard deviations. And when that happens, it assumes that it got the baseline wrong, that is an untrustworthy fit, and it throws it out and it will warn you. One event too short just means that one of those events fell below our 10 microsecond minimum event length window and was thrown out as a result. But generally speaking, a 90 or above % fit is perfectly acceptable. We can go back through if we want and play with some of the settings to try to change the number that differ by baseline. But generally speaking, I'm satisfied with this as an example. So I'm going to pause here, and in the next video, we're going to go through actually visualizing some of the fits we found from this event and starting to post-process and look at how to segment our data sets.